Imagine you run one of the biggest AI labs in the world, and one of your own internal deployments does something you didn't want it to do. Not a customer incident, an internal one, the kind nobody outside the building would ever learn about. You have two options. You can fix it and say nothing, which is what almost every company in history has done with almost every internal problem. Or you can write it up and publish it.
And the second option costs you something every single time. Competitors quote it back at you. Journalists compress it into a scary headline. Regulators file it away. There's no obvious upside.
Which is why today's lead is interesting. OpenAI has published a post describing safety and alignment issues they observed in their own internal deployments. The published artifact behind the model pause we covered yesterday from second-hand reports. It's Wednesday, July 22nd, and here's the root for today. That disclosure and what it says about incident reporting norms. Then Nvidia's Vera CPU and Carl Freund's argument that it's a run at the entire server CPU market. Then a strange day on the Linux kernel security list, over 400 CVEs in 24 hours. Then a research pair on coding agent harnesses that I think is the most useful thing on the show today, and we'll close with a book.
The detail that caught me first was who boosted the post, more than the post itself. Jack Clark, Anthropic co-founder, the person who writes Import AI, a competitor's safety lead, flagged it with approval and named the counter-incentives against publishing material like this.
It matters that when yesterday's story broke, everything we had was second-hand. People describing a paused model and sandbox containment behavior, reconstructed from fragments. Today, the primary document exists. OpenAI chose what to disclose in its own words on its own site.
And the choice to publish is itself the news. Think about aviation. Planes got safe because the industry built a culture where incident reports get filed, shared, and read by rivals without anyone treating the filing as an admission of guilt. Software security got partway there with CVE disclosure. Frontier AI has had nothing like it.
Right, and until now the incentive structure ran hard the other way. If your model does something concerning in an internal deployment, publishing that fact hands ammunition to competitors, plaintiffs, lawyers, and every politician looking for a hearing soundbite. Clark's point, as I read it, is that OpenAI ate those costs voluntarily.
There's also a reason the internal dash deployment part specifically matters. The labs run their newest, least constrained systems on themselves first. Internal coding agents and internal research assistants, so the strangest behavior in the world shows up inside those buildings months before any customer sees it. If that layer stays dark, the public record of model behavior permanently lags the actual frontier.
Which makes a disclosure from exactly that layer more valuable than a post-mortem about a shipped product. So does one post make a norm?
Only if it's reciprocated. One lab publishing one post is a gesture. Two labs publishing on a cadence, with rivals citing each other's reports the way Clark cited this one, that starts to look like an institution. And notice Anthropic's safety lead praising it publicly is itself a move in that game. He's raising the cost of the next lab staying silent.
A voluntary disclosure is also a controlled disclosure, though. That's the harder, skeptical read. OpenAI decided the scope, the wording, and the timing. We learned what they chose to tell us about their internal deployments, and we have no way to know what the denominator is.
Sure, but that critique applies to every disclosure regime at birth. Early aviation reports were self-serving too. The mechanism that fixes it is repetition plus outside pressure. Once you've published 3 of these, the 4th one that conspicuously omits something becomes its own story. The trap would be treating a controlled first disclosure as a reason to prefer zero disclosure.
And there's a policy backdrop that makes the timing legible. We've spent the last week covering Gold Eagle, the Federal Clearinghouse story, and the FINRA-style regulator proposal. If mandatory incident reporting is coming, the lab that can point to a voluntary track record gets to help write the rules. The lab with nothing on file gets rules written at it.
Voluntary disclosure as regulatory positioning. That's the generous read and the cynical read in one sentence, and I think both are true. My open question is granularity. If the write-up just says we observed concerning behavior and mitigated it, the field learns very little. If it says here is the deployment context, here is what the model did, and here is what our monitoring caught and missed, That's the aviation report version, and that's the bar I'd hold the next one to.
I land there too. The first disclosure gets graded on existing. The second one gets graded on specifics. Let's move to hardware. Carl Freund, longtime chip analyst, writing in Forbes yesterday, published a piece arguing that Vera, Nvidia's CPU, is a deliberate run at the server CPU market rather than a companion chip for GPUs. His headline makes the claim outright. This chip is core business for Nvidia, not a sideshow. And the market he's talking about is roughly $200 billion a year, territory Intel and AMD have owned for decades.
The numbers he assembles are the story. He cites Bank of America estimates of 4 to 5 million Vera CPUs shipping in the second half of this year, against about 2.5 million Grace CPUs total, ever. And they project $20 billion of 2026 revenue from Vera alone, at an average effective price somewhere around $30,000 to $40,000 per CPU, once you count the memory and the surrounding system.
$20 billion would make the CPU side business, on its own, larger than most semiconductor companies, and it recolors Grace in hindsight. Grace always read as a support part, a way to feed the GPU. Freund's argument is that Vera gets bought on its own merits. What's his technical case?
He leans on a few specifics. Roughly 2 times faster single-threaded performance than AMD's 128-core Turin parts by his account, a memory fabric with about a 5-fold latency reduction, and 5 times the memory bandwidth per watt out of LPDDR5, and it's monolithic, no chiplet boundaries, so no performance tax at the seams. His argument is that this profile happens to match what agentic AI workloads want, lots of fast serial work orchestrating the GPUs, with memory latency as the constraint.
He also brings customer evidence, which is where analyst pieces earn or lose me. Perplexity reporting 1.5 to 1.9 times the performance of x86 on agentic workloads. The New York Stock Exchange reporting a 6-fold improvement in tail latency on streaming. Los Alamos seeing 3 to 7 times on scientific simulation. Those are the customer's numbers as Freund relays them, so the usual caveat about vendor-friendly benchmarks applies.
Even discounted, the competitive picture holds. If the CPU that sits next to the GPU is also Nvidia's, then Intel and AMD lose more than a socket. They lose the argument for being in the rack at all. Nvidia already owns the accelerator, the interconnect, and the networking. Vera closes the last general-purpose gap.
And there's a buyer-side consequence I keep turning over. Every hyperscaler spent the last 3 years building ARM CPUs to escape exactly this kind of single-vendor dependence. Graviton, Axion, and Cobalt. If Vera is as good as Freund says, the price of escaping Nvidia goes up at the exact moment the dependence gets deeper.
One thing on sourcing, though, this is one analyst's synthesis, not an Nvidia announcement, and the shipment forecasts are a bank's model. What would firm it up is a cloud provider putting Vera in a general compute instance type, sold for workloads that have nothing to do with AI. That's the moment it stops being a companion chip in fact rather than in positioning.
Something odd happened on the Linux kernel security list today. The kernel's CVE announcement list published over 400 CVEs in a single 24-hour window. That's the raw fact, straight from the lore.kernel.org archive, and it made a small Hacker News thread where commenters started asking the obvious question: is automated analysis, model-assisted bug finding, now driving the volume?
Some background makes the number less apocalyptic and more interesting. The kernel became its own CVE numbering authority back in 2024, and Greg Crow-Hartman's position has always been that in the kernel, essentially any bug fix could be a security fix, so they assign CVEs liberally rather than litigating severity. High daily volume is partly policy, not purely discovery.
Right, so 400 in a day is an outlier, even against an intentionally generous baseline, and the model attribution comes from the comments section, not from the kernel maintainers. Commenters describe a pattern of narrow, cornered findings, the signature of automated scanning. We should hold that as community suspicion, not established fact.
But the downstream math doesn't care about attribution. Every one of those 400 entries shows up on somebody's compliance dashboard. Enterprise vulnerability scanners don't read the kernel's philosophy statement. They count open CVEs and flag the fleet red. A security team at a bank now has 400 new line items, most of them irrelevant to their configuration, and the work of proving irrelevance falls on humans.
That's the asymmetry we talked about on Tuesday from the attacker side, showing up on the defender side. Discovery is being automated faster than triage. A model can corner a bug in minutes, deciding whether that bug matters for your kernel config, your distro backports, and your threat model is still an afternoon of a skilled person's time.
And the interesting second-order effect is on the CVE system itself. It was designed as a scarce signal. A CVE meant a human found something and judged it serious enough to name. If automated discovery makes CVEs abundant, the signal has to move somewhere else. Exploitability scoring, reachability analysis, or distro-level curation. Somebody rederives scarcity one layer up, or the whole channel turns into noise.
The number to check next week is simple. Was this a one-day spike from a batch submission, or the new daily baseline? Those imply very different futures for everyone downstream of that list. Now the research pair, and the first paper is the one I'd hand to anybody who ships with a coding agent. It's a longitudinal study headed to the journal TOCEM, and the design inverts the standard experiment. Everybody benchmarks different models inside a fixed agent harness. These researchers froze the model and varied only the harness. 35 sequential releases of the Qwen Code CLI, each run against 50 stratified SWE bench verified tasks with the same underlying model every time.
So any quality movement across those 35 releases can only come from the middleware, the system prompts, the tool definitions, the context management, and the loop logic. The layer everybody updates constantly and nobody controls for.
And the headline finding is a null result with teeth. Across 35 releases, no statistically significant improvement in resolve rate. The paper says early versions sometimes outperform their more sophisticated successors. Meanwhile, the cost side moved a lot. Later releases consume nearly double the tokens and tool calls for the same outcomes.
Double the tokens, flat quality. If you felt like your agent got slower and hungrier over 6 months of auto updates without getting smarter, this is the first controlled evidence that the feeling can be the harness. And the paper opens with exactly that observation. Practitioners report regressions after updates and blame the model because the harness updates itself in the background without asking. There's a screenshot in the paper of the update notification doing exactly that.
They also characterize the development culture that produces this, and they coin a term for it, hyper-churn. The 5 harnesses they surveyed, Codex, Qwen Code, Gemini CLI, Open Code, and OpenHands, average up to 18 releases per week. Dozens of commits a day, median pull request review under 4 hours, and thousands of open issues within months of launch. Bug fixes are about 30% of all commits. Stabilization and feature work running in parallel forever.
The architectural section is the actionable part for me. They mapped every commit to a reference architecture and asked which components correlate with regressions. 2 came out high risk. The model provider layer and context management, the components that directly govern what the model sees. Changes to extensibility and security components were consistently neutral, so the danger zone is precisely the code that touches the conversation the model receives.
And here's the sentence from the paper I found alarming. Every concrete example of quality degradation they documented had passed all existing automated checks. The unit tests were green. The integration tests were green. The regressions are emergent effects of harness model interaction, and nothing in these projects' CI is built to catch them, because running a benchmark suite on every merge costs real money.
Which is exactly where the companion paper walks in. Same archive batch, opposite temperament. It proposes falsifiable release gates. Every new capability in an agent runtime ships behind a pre-declared, machine-checkable acceptance suite, and a small set of standing invariants must hold across every release. The acceptance test is written before the feature. Their phrase is gates before code. A feature exists only once its gate passes.
They built it into an open runtime and then went further than a position paper. They followed their own system through 6 subsequent releases and reported whether the guarantees survived. The core action safety invariants held unchanged across all of them, while the test suite grew from 122 tests to 563, and they insist every invariant ship with deliberately broken models the checker must reject. Their line, "A checker that cannot fail proves nothing."
The concrete result that made me sit up is the self-improvement one. The gated loop compounds a small model from 20% to 70% held-out accuracy, and along the way it rejected, with no human in the loop, a candidate update that only inflated the model's confidence without improving accuracy. The gate caught a confidence gaming update on its own, and the whole governed path costs 0.021 milliseconds per request, about 0.008% of inference time. The overhead argument against this discipline is gone.
Put the 2 papers side by side, and they're one argument from opposite directions. The first documents what agent middleware development looks like, with no acceptance discipline, enormous effort, flat quality, doubling cost, and regression sailing through CI. The second demonstrates that a pre-declared, machine-checked discipline can survive a real roadmap without ossifying. It rhymes with the proof or stop lifecycle material we covered on Saturday, but this is the first version with longitudinal receipts.
One caution for anyone racing to cite the first paper in a vendor argument. The controlled study is one harness, Qwen Code, on 50 tasks. The hyperchurn characterization spans 5 projects, but the null result is narrower than the headline it'll get. It deserves replication on Claude Code and Codex before anyone treats it as a law. My bet is it replicates, and I'd love to be wrong in an interesting direction.
Either way, the practical advice in the paper survives the caveats. Pin your harness version, report which version you benchmarked, and when quality drops after an update, suspect the update before you suspect the model. Last item, and it's a warm one. Nathan Lambert announced yesterday that his book is finished. It's titled Reinforcement Learning from Human Feedback, and it's the reference he says he wished had existed when ChatGPT arrived. The post-training, fine-tuning, and alignment handbook the field has been passing around as scattered blog posts and tribal knowledge for 3 years. There's a companion course and a free web version alongside the physical book.
Physical copies are already out in the world. Greg Kamrat posted a photo of his yesterday afternoon, and I think the timing gives the small item a little resonance. Post-training was an oral tradition. You learned reinforcement learning from human feedback by being in one of maybe 5 buildings or by reverse engineering papers that skipped the details. A canonical, citable text means the craft moved from apprenticeship to curriculum.
It's also very on brand that the person who wrote it down is the person who spent 3 years narrating post-training in public. Lambert's newsletter has been the closest thing the field had to a running textbook anyway. This binds it.
So that's the day. A lab publishing its own problems, a chip analyst calling a $200 billion land grab, a security channel drowning in its own success, and 2 papers arguing that the layer between you and the model deserves the same engineering rigor as the model. Thursday, I want to see whether the kernel CVE number was a spike or a new baseline.
And I want the second OpenAI disclosure whenever it comes, because that's the one that tells us whether this week started a habit or exhausted one. This has been Braid. I'm Lenar. See you tomorrow.